Hi everyone, today we are going to learn about wave-particle duality. So what is actually wave-particle duality? You have learned that about duality nature of light, where light can be a particle or can be a wave nature. So in particle nature of light, we know that light is incident on a metal surface, and this light will have a quantum of energy which we call as a photon, and this photon will have a packet of energy which is equal to hf. Is equal to hf. So this hf is greater or equal to w, then your electron will be emitted. If your hf is less than w, then electron will not emit. So what is W? So W is actually the work functions of matter. So work function is the minimum energy that required to remove or emit electrons from the metal surface. So this is called photoelectric effect. So photoelectric effect is the experiment that proved that light can be a particle nature. While light also is a wave nature, where we can prove that by using interference pattern or diffraction patterns, which means that a light is incident on slits and interference pattern will form on the screen with constructive and destructive interference happen. So this proves that light can be wave nature. So according to this theory, means that every matter will also can be a wave nature. In other words, if light initially is a wave, can be a particle, then initially as a particle can also be a wave. So according to Louis de Broglie, so here we pronounce it as Broglie. Okay, this one pronounce it as Broglie. Louis de Broglie. So according to Louis de Broglie, so this theory, duality of light, is reversely using for the matter particle. What does that mean? So according to the de Broglie hypothesis, all moving particle has wave nature and it has wavelength. In other words, it's the reverse of the light. So now particle initially is the particle. It can be also as a wave nature, means it can be either as a particle or either be a wave. So since this particle can be a wave, then it must have a wavelength. So this wavelength from the de Broglie hypothesis we call it as de Broglie wavelength, which can be used the expressions of this lambda equal to h over p, where h is your Planck constant 6.63 times 10 to the power of negative 34 joule per second, and p is the momentum of the moving particle. So through this hypothesis, de Broglie hypothesis, that wins the Louis de Broglie awarded a Nobel Prize in the year 1929. So it means that this theory is quite famous and very useful in physics field. Okay, so now let's say you have this equation lambda equal to h over p, and then we have a moving particle here, which is your electron as a moving particle is isolate from the negative plate to the positive plate. So this electron will gain kinetic energy, which is equal to half mv squared. Okay, it will gain energy which is equal to half mv squared, and you have this equation 1, and let's say your equations of lambda de Broglie wavelength, which is equal to h over p. So lambda will be equal to h over mv because p is equal to mv. Then according to first equation, this equation can be rewritten as v equal to square root of 2e per m. So this one becomes second equation, this one is third equation. Then you substitute 2 into 1. If you substitute 2 into 1, then your de Broglie wavelength will be equal to h over m square root of 2e per m. In other words, your lambda here, use other color, so lambda here can be written as h over square root of 2me. So after you simplify this one, then you will get this one. So this is your de Broglie wavelength in another expressions. So of course, if the electron is accelerated from negative flat to positive flat with potential difference V, then the kinetic energy gain can be written as EV. So this equation now will become lambda equal to h over 2 MeV. So V is your potential difference. So it can also be written as this one. So from these two, you will see that the lambda or the de Broglie wavelength can be affected by the mass of the moving particle and also the energy gained by the particle. Okay? So we can make a conclusion from the de Broglie hypothesis where wave-particle duality, where all the particles or both the matter and light can be possessed as a particle-like properties under some situations, and also it can be a wave-like properties under another situations. So means that in different situations the matter will become a particle-like or wave-like nature. It will depend on the situation or the phenomena. So if the phenomena wants it to become a wave, then the particle will become a wave or the light will become a wave. If the situation wants it to become a particle, then the particle will become a particle or the light will become a particle. Okay? So you may ask that any proof for wave-light duality, we don't want just a theory for that. Okay, so this person, G.P. Thomson, did a first experimentally prove that the wave-light duality is actually correct. Okay, so through an experiment, we call it as a electron diffraction experiment or cathode ray diffractions. So we know that for a wave, if we want to prove that something is a wave, we can prove that by observing the interference pattern. So just like light do, so when a light is incident on this double slit, it will form an interference pattern at here on the screen. Okay, there is a constructive interference and destructive interference formed on the screen. So now, if you replace this light with electron, let's say you replace this with electron, so we know that electron is actually a particle. So initially, we only know that electron as a particle. So if according to particle-like properties, so the particle will just pass through the slits, and when it passes through, because it's a particle, so there's no diffraction, then it will just go straight through the slit and form two spots here. Means there are only two spots, no diffraction or no interference pattern. But from G.P. Thomson, it proved that from the cathode ray diffraction, so what is cathode ray diffraction? It's actually the experiment that doing diffraction pattern as what you have done in your light, but in just a special apparatus which we call it as a cathode ray. Because if you want to inject electron, so you have to inject it in a cathode ray. So this one is your electron gun, and this one is a thin metal foil. So what is this thin metal foil used to? Later I will discuss. And inside this cathode ray tube is a vacuum chamber, and here is a screen. So what is actually thin metal foil? So let's say electron is being ejected from the electron gun. So it will travel with a very high velocity, which is almost equal to 10 to the power 7 meter per second, which is quite near to the speed of light. So when it's traveled with v, so according to lambda over h over p, then the de Broglie wavelength for an electron will be very small, which is almost equal to 10 to the power negative 11 meter, which is really very small compared to the wavelength of light. So your wavelength of light is actually equal to 10 to the power of negative 7. So compared with this one, this has a very small wavelength. So in order to let the electron have diffraction pattern, the slit here must be in atomic scale. So atomic scale is too small. So how can this experiment be done? So it just insert a thin metal foil, where thin metal foil has an arrangement. The atom will be arranged in this lattice form. So this lattice form will act as a diffraction grating for the electron to pass through. If electron is a particle, then it will just pass through and without diffraction. But now, because it's with particle duality, so this electron will be diffracted. Okay, it will be diffracted. The electron will be diffracted, and these two waves will have a path difference. So when there is a path difference, then it will be a constructive or destructive interference formed on a screen. So instead of forming only two spots here, which initially we only predict that electron is just a particle, that G.P. Thomson come out with a result that there is not two bright spots. Instead of two bright spots, he gets that the interference pattern of the electron is almost the same as the X-ray interference pattern. So this is your X-ray. So we know that X-ray is a electromagnetic wave. So electromagnetic wave can be also a particle. So it's actually almost the same as an X-ray, but it's slightly different. So this one is your electron diffraction pattern. So this has proved that it's not a particle-like circumstance. So now electron is a wave. Okay, so you have already proved that, G.P. Thomson have proved that electron can be a wave through the cathode ray diffractions. Okay, is it clear? So now you have already known that all matter can be either wave-like properties or can be either particle-like properties. So through this understanding, later they developed the electron microscope. Okay, before we go for electron microscope, if you want to understand more about cathode ray diffractions, you can click on the link that I put on a description box. So this link, YouTube link, it will show you the experiment for the electron diffractions. You can have a look on this YouTube video. It's quite good, so you can understand it. Okay, so you just click on a link that I attached on a description box. So after you have learned the wave particle duality, so this theory have come to a development of the electron microscope. Okay, when we talk about microscope, means it must have a very good or very high resolving power. So what is actually resolving power? In your previous chapter, we already learned about resolving power. Resolving power is the ability to distinguish two nearby objects, which we can see a very clear object when we have a high resolving power. Okay, so in order to increase your resolving power, because we want electron microscope with a very high resolving power, then we have this equation that will affecting your resolving power. This equation is the equations of your interference pattern for your constructive interference. Okay, so if you want to have high resolving power, then you have to decrease the value of psi theta. So in order to decrease the value of psi theta, lambda have to be very small, or you decrease the value of the wavelength of the sources. Okay, so from the classical microscope, which we call as an optical microscope, like this one, so this one they use the source of light, means they use light to see the specimen here. And this one, electron microscope, is using ejections of electron. So you have learned wave particle duality. From that, if an electron which is travel with the velocity of nearly equal to 10 to the power of 7 or nearly equal to the speed of light, then it will have a wavelength which is 10 to the power of negative 11 meter. If compared with light, light will have a wavelength 10 to the power of negative 7 meter. So if comparing these two wavelengths, electron will have a very small wavelength than light. So when you have very small wavelength, so sine theta will decreases. In other words, your resolving power of the electron microscope will be greater than resolving power of optical microscope. So in other words, from this wave particle duality, they come up with the development of electron microscope using the wave natures of the electron to produce the interference pattern in order to increase the resolving power of a microscope. So now you have two types of microscope. Of course, there is advantages and disadvantages between these two microscopes. So what is the difference between these two microscopes? So we have this electron microscope. So for electron microscope and optical microscope, so electron is from the source of electrons. So it means that when you observe the specimen, you need electrons. But for optical microscope, it's only light. Okay, if you want to observe the specimen, you only illuminating light on the specimen. And then, because electron microscope need to produce electrons, so they need tungsten filament to produce electrons. But for optical microscope, there is no filament used to produce the light source. And then what is the advantages for electron microscope? Because now we know that for electron microscope is actually using electron to observe or to see the specimen. So in other words, electron have a very small wavelength compared to the wavelength of a light. So it has very high resolutions, which is about 250 times higher than light microscope, so or optical microscope. So this optical microscope has the disadvantages, which is a very low resolutions compared to the electron microscope. And the advantages for the electron microscope is we have a higher magnification, which is up to 2 million times. And then for optical microscope, it's only up to 2000 times. Compared to electron microscope, optical microscope is lower magnification. So we want a good purpose in order to magnify your specimen, then you use electron microscope. So of course, for electron microscope, if you look at the structure there, it's very heavy, it's very big compared to the optical microscope. So there is a lot of disadvantages in electron microscope. First, it can only observe that specimen. Okay, it cannot observe living specimen or moving specimen. Unlike optical microscope, it can either see the live one or the dead one. Means that either the specimen already died or is still living, then it can observe by optical microscope. Not necessarily must be dead one. So any moving specimen can be seen. And then we have another disadvantages for electron microscope, which the image or the image formed from the electron microscope is only in black and white, because we know that electron doesn't have any color. So the image formed on a screen is only black and white. Unlike optical microscope, the image has color. It's color because the incident source is light. Okay, and then another disadvantage is because it want to eject electrons to produce the observations of your electron microscope. So it requires vacuum chamber, just like your cathode ray tube. So it requires a vacuum chamber for observations. Unlike optical microscope, you no need any vacuum for observations. So vacuum is not required in your optical microscope. And then if you want to eject a very high moving electron, then you need a very high voltage to eject the electrons. So optical doesn't need any ejections of electrons, so no need a high voltage of electricity. And for electron microscope, there is a risk of radiation leakage. In optical microscope, there is no radiation. Okay, and if you see through the diagram or the figure here, you will see that electron microscope is very compact and very big. So it's actually very difficult to use because you need to program it. You need a computer to process your analysis, your image. So it's actually very difficult to use, and it uses computer to do analysis. Unlike your optical microscope, it's very easy to use. You just see your image through the eyepiece or through the lens, then you will see the image. And you see electron microscope is very big and very compact and it needs computers, so it must be very expensive compared to optical microscope. Is rather cheap than electron microscope. So for the last point of your electron microscope, the disadvantages is the sample or the specimen must be completely dry. If it doesn't dry, then it cannot do any observations. So this is the second topic of this chapter. I hope you can understand what I'm deliver here. So that's it for today. So I will see you in my next lesson. Thank you.